All right. So, are we ready to get started? Gentlemen, are we listening? Yes. All right. So, we are now bridging on to our spec internal. This one's worth 3 credits. And like I said, it is very puzzle-like. So the idea of what you're going to get in this assessment is you're going to get 3 bits of data, and these 3 bits of data will tell you what organic molecule you have. So the first bit of data that you're going to get is something called the IR spectra, which is this first one up here. That's the one I'm going to be talking about today. The second bit of data on these sheets is something called CMMR. Do you want me to label these? Yeah. So we start knowing what these are referring to. So this one's IR. This one is CMMR. I'll talk about that one next week. This one on the bottom is mass spec. So from these 3 bits of data, you'll be able to figure out what molecule you have. Does that make sense? So 3 bits of data, 1, 2, 3, and from there you'll be able to figure out a molecule. Just like when we were talking about the NCA exam questions last week and how we were decoding the information and all the little hints and how each little hint told us something about the molecule, it's a similar sort of thing. So if you guys notice, each question in this book is the same setup: IR spectra, CMMR, mass spec. IR, CMMR, mass spec. So each one of these things is a different molecule. CMMR. Are we okay with that so far? All right. Now, when we are looking at these questions to figure out this molecule, there are 2 main things we need to ask ourselves in order to solve the molecule. The first question is, what functional group is there? And the second question is, how many carbons do I have? Once I have those 2 things answered, I will be able to then start proposing potential molecules that could fit those parameters. And the data will back it up. Are we okay with that so far? It's the 2 first things we have to answer. Cool? Keep going? All right. So this first question here, what functional group is there? There are 2 ways we're going to figure that out. The main way we are going to figure that out as our first go-to point is using the IR spectra. So the IR tells us functional group. Cool. All right, keep going. All right. Now, let's have a look at what IR is and how does it work? All right, can I move it? Okay. So I'm moving now to this packet here to kind of explain what IR is. And then we're going to go through and look at some different examples of the IR spectras. So just grab a color so that way it's, all right. So first off, have you guys heard of the electromagnetic spectrum? No, yes. It's something that's come up in physics. It would have come up when you guys were talking about light. So the electromagnetic spectrum is just talking about the different types of light that we have. Light is categorized by the size of the wavelength. So we can have really big wavelengths, like the size of buildings. Those are radio waves, which is what we listen to in the car. We could also have really tiny wavelengths, such as gamma rays and X-rays, which are very high energy and very small. So that's the range of the electromagnetic spectrum. Are we okay with that so far? Hopefully that rings a bell. The other way we can describe them is frequency. So how often does it have the little squigglies coming through? And there's a huge range of sizes. The smaller they are, the more energy they have. What we can see with our eyes is the visible light. So it's a very narrow area of the spectrum. On the two opposite ends of where we can stop seeing is the infrared. So basically red is on this side. And then the ultraviolet, so violet's on that side. And then we can just see this small little band of colors. Are we okay so far? All right, so this first type of spectra that we are talking about is the IR spectra, which stands for infrared. So we are using the wavelengths from the infrared section of the electromagnetic spectrum to learn things about our molecule. Cool. All right. So the way this machine works is basically I have a little piece of plastic that we call a cuvette. It's a fancy word for that. Now, you don't need to explain how the machine works. I'm just explaining how the machine works so that way you understand what the data means. So what happens when we are using the IR machine is that we shine a light at my sample of my molecule. And then what I do is we are seeing how much of that light gets absorbed. And then we test this at different wavelengths in the infrared. We good so far? So we have this one cuvette sample, it shines one light at it, and then shines the next light, and then it keeps going through the whole spectrum of that section, shining different wavelengths of light and measuring how much is absorbed. And what we then get is this data at the end. So this is our data output from that. So you can see on the bottom here, it has the wavelengths. So these are the range of wavelength sizes that we test. These ones are the very short ones. These ones are the very large ones. And then on this side here, we have the absorption. So we're seeing how much of that light is absorbed. So the deeper the trough, the more light is being absorbed there. So that's what this little, like, you can call them peaks, you can call them troughs, but the idea is like how much of it is being absorbed. Are we absorbing most of the light? Are we barely absorbing any of it? Yeah? Now the cool thing about this process is that different functional groups absorb light at different energy levels. So we can use that as a way to figure out what functional group is in that molecule. When it comes to looking at these, and you can see here, it's already laid out some of the ones to kind of look for the ranges that you'd expect to see them at with the resource sheet that I gave you guys. Once I can find it. There it is. So on the resource sheet that I've given you, you can see that we have one that's labeled for IR spectra, and it has the list of all the different functional groups, and it has a range of where you would see the trough to be at. So that's just kind of giving you an idea of where to look for it. So you will get this resource sheet on the assessment. Okay? Phew. The other thing that I find helps is looking at a lot of images when it comes to the different functional groups, because this does give you an idea, but if you guys notice, a lot of these functional groups overlap in their wavelengths, and so you need to be able to distinguish which one's which. Some things to keep in mind is that we tend to only look at 1500 and above, so this section of the IR spectra. The problem with the lower section is that it's really hard to kind of distinguish the functional groups and the peaks and troughs that are there, simply because there's a lot of other background noises. So we are primarily going to be looking at this section when it comes to labeling it, but you will notice that on this, it will mention stuff that's below 1500. But for argument's sake, I'm not worried about it. All right, we okay so far? Okay, so let's now start looking at some of these spectra. For a very long time, these guys are going to look like squiggly lines, and then eventually you'll just click and you'll be able to see them very clearly without any second guessing. All right, so this first IR spectra that I've given you is an example of an alkene. So that's that C double bond C. It's really hard to see on the IR spectra. You can see that the C double bond C is noted here, and that's near that kind of 1500. It's not a very distinctive peak because there's lots of peaks that look like that. I should say troughs actually. There's lots of troughs that look like that, so it's really hard to kind of pick out. The other thing that they point out that you could possibly identify it with is the carbon-hydrogen peak. So this is a carbon-hydrogen with a carbon that has a double bond. So if it was this, you wouldn't see that peak. So that's what that's referring to. This one's really hard to see. I wouldn't expect you guys to find it on the IR very easily. What I would expect you guys to do for this IR is to look at the molecular formula. So what I would give you in this case, because this IR is so hard to find the function group, is that I would give you the molecular formula, or I would give you an empirical formula. And from that information, you would be able to tell by the ratio of carbon to hydrogen which one it is. So if you guys remember, for an alkene, the ratio is for every one carbon, you're going to get 2 hydrogens. So that's the hint to find that guy. So basically, I'd be looking to see if that's the ratio. So that one, unfortunately, is a very bad example to start with. But that's what an alkene looks like. All right. The second one that I have here is an alcohol. The alcohol is this OH, and it's a wide stretch. If we look at our resource sheet, it's somewhere between 3,200 and 3,500. So if I look at my numbers here, 3,000 is about here. So I see that it's coming in that area. So that's what I'm looking for an OH. And it's quite a big trough in comparison. What you can do to help you kind of get a reference point of location is looking for the CH. So CH has because you know that all organic molecules have to have a CH. That's just how the organic molecules are built. So those guys are typically around 2,800 to 3,000. So this here is an example of a CH. So that's a really good kind of reference point to kind of see where things are located in reference to that. So that's my CH, that's my OH. If I look over here on this first one we did, this here is my CH. And if I look above, I don't see that same trough there. So that tells me that this doesn't tell me alcohol. Does that make sense? It's going to look like a squiggly lines for a little while, and then it's going to suddenly make sense. Are we okay with that so far? All right, keep going. It might help to see all of them and then backtrack. All right. On this next page here, again, we can see our CH. That's my reference point. And this is my main peak at 1,700. So if I look over at my resource sheet, 1,700 is very common for the carbonyl, the C double bond O. So that here, and it's a very sharp peak, that's my C double bond O. So what that tells me is that C double bond O, I think about the functional groups that could have a carbonyl. So that could be an aldehyde or a ketone. Part of this assessment is not only identifying what is there, but what is not there. So what I can notice when I look at this is I have my CH peak. I look over and I'm looking to see, does it have the alcohol troughed? And I don't see it there. So what that tells me is that there's no OH in this molecule, so it's not a carboxylic acid. Because carboxylic acids, I know, have the carbonyl. And I'll show you guys a carboxylic acid so you guys can see the difference. This one here is another example of the C double bond O. This one is either an aldehyde or alkene. Sorry, aldehyde or ketone. I have my CH here. Now I have this peak here, but that peak there does not match what an OH peak looks like. So that one's probably just some background or something with going on in the molecule. This is actually not a peak that I'm looking for. And I'll show you guys what I mean by like what it should look like if there's something there. So these are two examples of the same functional group. I just want you guys to notice that it's the same functional group, but they might be slightly different. And that has to do with the organic molecule itself and what else is attached to it and where these functional groups are located in the organic molecule. So it's kind of, it's a guideline. I know you're confused. You got to see a lot of these and then they're gonna make more sense. All right. This one here, you see how again at 1700 I have a peak? So that's my carbonyl. This is probably the hardest spectra to understand. Huh? Yeah, go for it. All right, again, we use our CH as a reference point. So that's this guy right here. And then this big trough is my OH. So something with a carbonyl and an OH, that is a carboxylic acid. You can see what's happening here is that this spectra looks like a combination between the alcohol and the carbonyl from the aldehyde. So that's how we can see that there's two functional groups there. Not two functional. There's two markers on the IR spectra and this functional, like the OH and the carbonyl. Now, some things to note that are slightly different with this guy is that this OH, you see how it's kind of shifted downward a bit. It's not as high on the, it's not as near 4,000. It's gone down a bit and it's kind of crashed into the CH. So in a normal alcohol, the CH is quite separate from the OH. In this case, it's kind of blended together. So that's another hint that we have a carboxylic acid. The other reason why I know it's a carboxylic acid is I have the carbonyl as well. Whereas with this one here, when I look at the alcohol and I look at 1700, there's no C double bond peak. So again, that tells me alcohol, not carboxylic acid. So for this assessment, I want you to think about what's there and what's not there and trying to figure out what's going on. And then, like I said, there'll be the two other spectra will help back you up. So that's my carboxylic acid. Good? All right, this one here is just an example of an acid chloride. I wanted to include it just so you guys know what they look like, but I wouldn't assess you on acid chlorides because, again, they're really hard to distinguish. So there, again, is my C double bond O. I can see my CH. I look and I see that there's no OH. So that tells me not carboxylic acid. This one here does have a carbon chloride peak, but again, it's in that fingerprint region, which would be hard to see. So I wouldn't assess this one, but just so you guys know that that's an acid chloride, if you guys are wondering. It'd be too hard. I'm just saying there's lots of carbonyls because of it's a very common functional group, or sorry, it's a very common structure in a lot of functional groups. All right, keep going. No, stop. This is yuck. It's going to look like squiggly lines for a while, and then eventually it's going to stop looking like squiggly lines. You just got to see enough of them, and then you'll notice it. Won't be assessed. Accessed. Assessed. Thank you. All right, next spectra. All right, this one here looks different. I know they don't look different to you guys, but they are different, I promise. All right, so markers that you should always use. Find your CH. So CH kind of has roughly around 3,000. So 2,800 to 3,000, you should see a trough there. And it's kind of like a squiggly like that. Like it's a multiple squiggly line kind of thing. Yeah? So it's a good marker because that way you can then figure out if it's like above or not. The other thing I would usually do is I would mark where 1,700 is, because 1,700 is where I would expect to see carbonyls. So I'm just basically seeing, is something there? So when I'm looking at that, do I see a trough that's at 1,700? Yeah, I see this one here. So that tells me C double bond O. All right. And do you see how I see a trough that's right next to my CH? So a lot of you guys are thinking alcohol, and you're thinking carboxylic acid, which is a fair thing to think because you guys are used to seeing that next to it. But do you see how this guy doesn't crash into the CH? It's separate. It also has these two double ones, whereas this one's just like one big one. It's going to be shapes, guys, just like primary school. So this here is actually an NH2. I knew it. It's going to look like squiggles for a very long time, and then it's not going to look like squiggles. All right. Do you guys remember which functional group has the NH2 and the carbonyl? Amides. So this is an amide. You're like, I don't like this. All right, next one. All right. We're looking at 3,000 to 2,800, so that's my CH. That's my reference point. The other thing I'm labeling is my 1,700. So this here is my NH2 because we can see that it's got that double troughed again. Do you think a carbonyl's here? No. This is one I purposely stick in because it is tricky. It looks like there's a trough there, but when you guys look at the other carbonyls, you notice how big that absorption is. It's basically almost at 100%. That one is nowhere near that. So this one's not a C double bond O. So what functional group would have that? Amines. So you see how this one is an amine, and let me just get the alcohol so you guys can see it in comparison. This is what an alcohol looks like. They look different. They have overlapping sections though. So if you look at your resource sheet, the alcohol, 3,200 to 3,500 roughly, and then the amines are 3,300 to 3,500. So they're roughly in the same ballpark, and so it's really important that you understand the shape of what they're supposed to look like to help distinguish which one's which. There'll also be other hints from the other spectra to help you back it up as well. All right, so that's what that one looks like. And then these are my last two, and these two are really yucky because I don't like them, but they do come up. All right, so again, use the CH as our reference point and look at where 1,700 is. So 1,700 is probably roughly around there. And now we're trying to identify things from it. Now, we don't see a carbonyl. So no C double bond O, because that would have happened around here. I do see this trough over here, and this actually is an amine as well. But this is only got the one hydrogen. So this one's a secondary amine, whereas the other one was a primary amine. And let me show you what I mean by the difference. So a primary amine, it has two hydrogens attached to it and two little troughs. So when I'm drawing up the molecule, let's say, for example, it would look like that. And do you see how this nitrogen is only attached to one carbon? Okay. That one right there. For a secondary, oh, do you guys, go back. And for a secondary, I'm going to draw a 3-carbon structure again. But for a secondary amine, what happens is that the nitrogen is in the middle of the molecule. Like that. So we see how this nitrogen here is attached to 2 carbons. And there's only 1 hydrogen then. So it's kind of counterintuitive in a sense, like it's attached to 2 carbons, but you only have 1 peak. The way I remember it then is it has only 1 hydrogen. Yeah. And again, that one looks different from an alcohol because the alcohol has that larger, deeper trough, and it's wider too. So these ones can come up. And then here's my last one that I want to show you guys. This one is a real mess, but it's important for you guys to see it just in case it comes up. So again, look at 1700. Is there a trough there? Yep, so that tells me carbonyl. Find where the CH is, and then you see how there's a trough there. So that's my NH. This one looks different from a carboxylic acid because you see how the carboxylic acid, where'd you go? Blends in like that, whereas this one still has it separate. So they're hard to kind of tell. You kind of just get used to it. So this is an amide that's secondary. Do you want a molecule of a secondary amide just so you know what it looks like? Sure. So it would be like CH3C double bond O and CH3. So that'd be an example of a secondary one where the nitrogen's in the middle. Whereas a primary amide, once I find my amide sheet, this guy would look like CH3, CH2, C double bond O, NH2. So that's the difference. The main thing you'll notice that if something's an amide versus an amine is that you see how much deeper this trough is. Trying to think what else I want to say about it. The other thing that you guys will have is the other spectra, and something else to note that you can then double check whether or not you have an amine or an amide is that the molecular mass will be an odd number. So if nitrogen's present, the molecular mass is an odd number. I'll just make that note here and I'll show you on one of the examples. So this data doesn't stand on its own, it does back each other up. And I'll show you what I mean on the practice problems that I gave you. IR is probably the hardest one to learn as a spectra. The data is the hardest to read. You really just need to see lots of IR spectra to know which one's which. But be mindful you do have the other data sets that you're going to get that can help you confirm if something's there or not. Are we okay? Can I move it? All right, so let's look at the practice questions that I gave you. So, like this one here, for example, when I'm looking at it, and I'll actually start writing on it with like the achieved merit or excellence. So right now we're just focusing on the achieved. So we're looking at 1700. And do I see anything there? No. So I write no C double bond O. I look for my CH as my little map guider. That's that guy over here. And then I have this peak here, or this trough. Alcohol would be the right guess. So this here is my OH. But let's say I'm not sure if it is the OH or not. I can then look at the mass spec data, and if this is an odd number, it confirms nitrogen. You see how it's an even number? Not nitrogen. So that confirms that we have an OH here. So this first question, number 1, I know that my molecule, whatever it is, has to have an alcohol. So therefore, alcohol from all that information. So we figured out the first question. What function group is there? And then tomorrow I'll talk about how to figure out how many carbons are there. Right, do you want to see another example? You want a break? All right, we can have a break. Take a moment. I have a GIM kit. Do you guys want to play GIM kit? Or you want to just have a little moment just to kind of digest what I said? Okay. A couple minutes. All right. Do you guys want to see another example, or you feel like you got it and you're ready to practice it? One more example? All right, we'll do question 2. The idea behind this as well is once you guys are able to solve a full problem, you can like pull apart the staples and like hand it in once it's done. So the idea is you're going to use all 3 spectra, figure out what the molecule is, justify it. But we're just doing the baby steps, which is identify. All right, so first thing we're looking at 1700. Oopsie. Well, I'm asking you, what do you think? That is a carbonyl. It is very, look at how sharp and that one is. All right, we're looking at our CH, and then I'm looking at the neighboring over here. Do I think anything's there? No. And if you're not sure, we can look at the other ones as reference points. So we know what an alcohol looks like. It's very, like, rounded. Also, if it was a carboxylic acid, it would have crashed into the CH. We know it's not an amine. Yeah, so it'd be an alkene or an ketone. Yeah. So no OH or NH2 or NH1. So on this assessment, it's going to be important to note what's there and what's not there, especially if you're aiming up for the excellence, because it helps us figure out what we have. So this is going to be either an aldehyde or ketone. It's not going to be a carboxylic acid. It's not going to be an amide.
What about
An alkene. So this one here, you see how deep that trough is compared to an alkene. Let me find that alkene. Where did it go, alkene? Oh, here it is. It's nowhere near as. Also, I would give you a hint. Like if I gave you an alkene, I would give you some hint to it because it's really hard to see it on a spectra. Let me find you one. Not that one. I know, like this one here, I'm giving you a hint because we're looking to see if there's anything at 1700. We see that when I do the math calculation, the hydrogen number is not double. So this one's I think an alkane. That's what I've given you here. So yeah, you kind of just, there's no good way to explain how to do it. You just got to kind of do it a lot. A lot of practice problems. That's why I've given you so many. All right, let me show you where some things are on Google Classroom that are useful, and then we can play, how much time we got? 5 minutes or 10 minutes? We can play a GIM kit so you guys can get used to kind of seeing those spectra. So, let's go to Google Classroom. And here we go to this guy. So I've started our spec topic. This is our first lesson. These are our key resources. So this one here has a link to the main page where all the lessons will be posted if you want the whole archive. But things that are useful, there's the checklist there, there's the resource sheet there, but this website here is where you can look up spec data, and that's actually really useful if you guys want to just get an idea of molecules and things like that, and just to see a lot of examples. So you can like type in things like molecular formulas or compound name, and you can actually pull up data to look at. So this is where I get all my data from that I make on these sheets. So I share that with you guys just so you guys can have a chance to look things up. The other thing on there is the combination questions. So I have a PDF file of the big packet that I've just given you. So if you want, you can also work on it online. Cool. All right, let's do some GIM kit so you guys can have a chance just to kind of look at spectra and learn them.